is I want to bridge a gap. We got 2 weeks left. I want to spend all 2 weeks in the same distribution, but I want to talk to you about distributions before we get to that distribution. So, what you've got,
Wow.
yeah, take a look at this. Well, you just briefly, because we're not going to explore the entire thing. What I'm showing you here, this is a great graphic that, not the pictures, but the graphic itself in the middle is a really, really wonderful graphic published by the American Journal of Statistics, Education of the American Statistical Association. I forget who published it. Doesn't matter who published it. What's cool about it is, what's really, really cool about it is, it shows you a lot of the distributions that are out there and how they're connected to each other. Like, for example, we talked about rolling a single die versus rolling 2 dice versus rolling 3 dice in Chuck-a-Luck versus buying 4 chickens. Each of those distributions is kind of its own special case. This kind of lists out the special cases that exist in the world. Now, we're not getting into hardly any of these. I learned a while ago, I used to actually, all the ones that I've drawn pictures of and drawn arrows to, I used to teach in 243. So, for example, an assembly line model, talking about a robotic arm that is trying to put a door on a car, or trying to put a rear view mirror on a door of a car, or trying to put the glass in rear view mirror on a door on a car, or trying to put the objects in mirror might be closer than they appear on a rear view mirror on a door of a car. All those things are computer generated. And they're computer generated via kind of physics and placement. And they generally are governed by what's called a geometric distribution. In other words, it gets to keep trying a fixed number of times. If it can't get the job done within that fixed number of times, it gets kicked out, and a human being has to come down and fix the problem. And that should happen once in a while. It shouldn't happen over and over and over. It should happen once in a while. And the idea of how do you define once in a while? Well, it's the geometric distribution. It's actually the distribution that's on the Gambler's Ruin quiz, although I don't make you actually calculate, I just give it to you. Geometric distribution is failure until success. Failure until success. Keep trying until you get the desired result, which is different than the binomial distribution. The binomial distribution says you get this many tries in order to keep track of what happens. The geometric says, keep trying until you get it right. That's what the geometric is all about. It's wonderful. It's also extraordinarily, as you can see, limited in its scope. It's off to this. The more off to the side these images are, generally, the more rare they are in the universe that we live in. Checking whether checks are fraudulent or not, amounts written on checks are fraudulent or not, actually is tied to something called Benford's distribution. It was used most recently in an Iraq voting. Iraq recently had a democratic vote. I say recently, I think it was 2008. Had a democratic vote. People were concerned about poll stuffing in Iraq, which is a perfectly legitimate concern. I think it happens all over the world, not just Iraq. But they invoked Benford's law, Benford's distribution, to see if the numbers that were coming in were legit or if they looked suspicious. And Benford's law allows you to do that. It has a distribution of digits. And this is, if you're interested, I can send you more information. There's a distribution of digits that should happen in things like check amounts, voting distributions, ages of people within a classroom, for example. You should see more 1s and 0s, and you should see 8s and 9s. Benford actually proposed percentages you should see. We tested in 244. But that's another example of a distribution. Powerball. Powerball, or that one from your quiz a few weeks back, the Pick 5 or Pick 4 from New York State. That was the hypergeometric distribution. I mentioned that in class, and there's a look at it up there. Modeling traffic patterns. How many of you ever sat at a light and gotten pissed off because it wasn't changing quickly enough for you? Now, sometimes that's just us being selfish. But sometimes, the one that drives me insane, and maybe this is just me, the one at Wall and Newport.
Yes.
That one seems to me to be off based on traffic patterns. I mean, that's the only one in town that truly frustrates me because I'm like, man, there's a line of cars on Wall. There is nothing on Newport, and it's been green. I'm timing it for 25 seconds. Like, that's stupid. Unless somehow that light is tied down the row on Wall Street to something else, which is possible. But that particular light, I think, in Bend needs to be looked at. I've actually written letters, but I haven't heard anything back. Of course. So that's actually tied to the Poisson distribution, which is a really, really fun distribution. It's like the binomial. Actually, it basically is a consequence, and you can see that it's actually tied to the binomial right there with the dotted line. It's a consequence of the binomial. If you have extraordinarily rare events, the Poisson generally fits them better than the binomial does. So the chance of a rooster is 10%. That's not really rare, correct? I mean, that's a pretty large chunk of percentage. If the chance of a rooster was something like 1 in 10,000, you're probably better off using the Poisson. I actually had to decide between those two for a court case I did about 5 years ago. Some kid got arrested for setting ELF fires, Earth Liberation Front fires, and I had to prove statistically that he wasn't trying to kill anybody by setting these fires. And generally, the research I did into ELF says they're not trying to kill people. They're trying to knock down structures they feel are impinging upon natural areas. So I statistically showed that the random chance of him not killing anybody by setting, I think it was 10 fires, was 0. In other words, he probably most likely was designing, statistically now, this is, statistically, it didn't imply that he was just setting fires willy-nilly. He was planning on setting them at certain times when he knew people wouldn't be around. So in other words, like burning down a ski resort in the middle of the night versus burning down a ski resort at 4 p.m. on a Bluebird Sunday. See what I'm getting at here? So that statistically, you can support it using the Poisson distribution, which is kind of a fun thing. Not that burning things down is fun, but just looking at it analytically is kind of fun. And then finally, the exponential distribution. The exponential, this is a super fun one, super fun. It's called the memoryless distribution. Certain things have no memory statistically, which means if you look at, say for example, a computer server, its age generally shouldn't affect its behavior. Now, generally, I say that. I logged onto my computer at home today, checked my school email at 4 a.m., damn thing locked up 3 times. Now, I know this is maybe a Windows thing, but I don't know anything. I have a theory that Windows has planned obsolescence built into their machines. So after you've got a PC for like 3 years, it becomes so clogged with crap, just by using it every day, that it becomes rendered useless. The exponential doubts that. It says, you know what, no, that should not happen. Well, maybe it shouldn't happen. Maybe it doesn't happen on things like servers. I think it does happen on things like computers, though. And look around. Look at some of these names that count you. Hyperbolic. I can't even read that. Something or other. Discrete Weibull. Weibul's a fun one. That's a fun one, too. That models infant mortality of machines. Have you ever had something you bought, a machine that broke almost immediately? You had to take it back for warranty repair? Yeah. That's not uncommon. It's not uncommon for machines to have high infant mortality. So you buy something and it's got this very steep death curve at the very beginning, and then it levels off and it works just fine, until at the end of its usable life, it then has a very extreme death curve because it wears out. And Weibull is a distribution, it's a U-shaped distribution. Fun. Again, I didn't bother teaching you guys all these because I could fill your head with like half a dozen of these things and test you on, but that seems kind of like a waste of time. I focused more on, if you switch to the next slide, that guy right there, the binomial. That's all we spent last week doing. And do you see how he's tied pretty comfortably right down to this guy called the normal? This is the other one. And the reason I want to talk about that one today, is twofold. First off, the binomial dealt with what kind of data? It helped us identify them, but in what kind of data? So we had chickens that I was buying, right? Said Max, go buy 4 chickens. And then I watched Max put shoes on his feet.
Uniform
It could be uniform. Look, bigger description than the individual. Because uniform's up there somewhere. Where is uniform? It's probably tied to the binomial, isn't it? Yep, they call it Bernoulli, but that's a uniform right there.
Either it is or it isn't.
Boom. Discrete. You guys are being very specific, thank you. But you're 100% correct. I was looking for a more overlying thing. It's discrete data. You count it, right? I watch Max and I say, how many times did he get his shoes on the right feet? We count the chickens, how many times? We count the number of games it takes us to win our dollar back. Those are all discrete. And many of these up here are discrete. That geometric was discrete, the hypergeometric was discrete, the Poisson is discrete. They're totally awesome. But what if you don't have discrete data? That's the problem. What if you don't have discrete data? What's the other kind of data? Continuous. What if you have continuous data? What do you do then? Well, you have to use a different distribution because you can't measure the binomial. You can't go, okay, I got 0.234552 of a bird because I measured it. No, you either did or you didn't. So we have to have a different idea there. But the other reason is this. I want to take a quick look back to the binomial. A quick look back to the binomial and show you the connection. So I put some simple examples up here. Flipping a coin, pulling a card out of a deck and checking its color, or boy or girl in the human race. All of these things have probability of what? 50%. 50-50, one half, 50%. 50, oh, no. No, is it the boy or girl one?
Yeah.
Well, what is it?
I don't know. I would just argue from a social justice standpoint that there are more than two genders.
Oh, gotcha. But statistically, there aren't because they're close enough to this. I see what you're saying, and I don't doubt that. But we can treat it as binomial statistically, not social justically. I made up that word. But statistically speaking, you can call it half because it's kind of like it's the same thing as the chicken binomial. Oh, speaking of which, thank you for bringing that up, Kelsey. I appreciate that. I want to show you guys that. I promised you this and never showed it to you. I constructed the distribution with, remember the 1 in 10,000 with the chick, the 1 in 10,000 chicks Gesundheit. So what I did was I went ahead and I made a new. Oops, you can't see that. I have to shrink it down. I made a new distribution. You know? Hang on. Over here. Let's make this column A smaller or bigger. I mean, oh, and then let's get in there. So what I did was I bought 4 birds. And I broke down, instead of just having roosters and chickens, but I had a third for other, I didn't know what to call it because it wasn't named anything in the article. So I could either get 4 of the others, I could get 3 others and a chicken, I could get 3 others and a rooster, I could get 2, 2, 2, 1, and 1, and so I just basically list out all, this is a trinomial distribution, yeah? A trinomial distribution versus a binomial, so you have that third possibility. The difference is the possibilities aren't yes or no, now it's yes 1, yes 2, or yes 3. But the trick is you have to have them adjusted for the possibilities of take out that 1 in 10,000. Now this is showing, it's not showing. Yeah, there it is. It's rounding it to 0.1, but actually it's not 0.1. It's 0.1 taking away that 1/10,000th, 1/2 of that 1/10,000. So I've adjusted the 0.1. It's not, you can see right now it's not rounding anything different, which means measurably it's not taking anything away from the 0.1. But that's okay, it's still accounted for. So if you look up in here, whoops, undo on that one, there we go. If you look up here, this is the distribution, accounting for all those other cases. But check it out, if you look at all the probabilities that include the other cases, they're basically 0, right? They're basically, because I'm only buying 4 birds. I'm only buying 4 birds. So 0, 0, 0. What I did was I highlighted in brown there the cases where we actually we're ignoring them, and I put them over here. Okay, and you'll recognize those from class. The chance of 0 girls, 1 girl, 2 girls, 3 girls, or 4 girls. There's the 5 outcomes. So here's all roosters, right? Here's all roosters, and there's the number you recognize from class, 0.0001. Compare it to this one, which is 0.000099, which is essentially 0.00001. Make sense? Here's one we got in class, 0.0036. Here's the one I got, 0.00359, which is 0.0036, rounded to a 10,000th place. Here's 0.046, remember this one from class, this is 2 and 2. 0.04854, which is, again, these are off by 1/10,000 essentially in each case. Does that make sense? 2916, 2914, 6561, 6559. So what I did then was I calculated the error of each, and this was that I sent back to my student. I never heard back from him. I was kind of bummed about that. Here's the error in the estimates. To a hundredth of a percentage, which would be a thousandth of a decimal, which means the overriding error in the entire distribution is 4 in 10,000, which is negligible. That's a negligible, so that's my point is, okay, I admit that that is out there, and I'm not saying it should be ignored, but for purposes of calculation, you can ignore it. Is that fair? So we can both kind of live with it, hopefully. And thank you for saying that. I totally forgot I had calculated this for you guys. Now you don't have to worry about trinomial distribution. You don't have to worry about any of this stuff, unless you take 244, in which case we'll worry about it together. But for right now, I just want to let you guys know you can look at that 3rd case, or 4th case, or 5th case. Veronica's like, yeah, great, that's awesome, I want to. And you don't have to, I'm going to shut it down right now. And go back to the good old statistical assumption. The good old statistical assumption that it's 50-50. Statistical. And if you don't like that one, use the cards. That makes it even easier. Pat?
Yeah, I was going to say the cards are 50-50.
Use the cards or the coin, make it even better. Take the genders off the table.
No, I mean the cards wouldn't they be 1 and 4?
Well, if you call red or black, it's 1 and 2. If the suit, yeah, 1 and 4. If you go rank, it's 1 and 13. But if you look at the colors, it's 1 and 2.
Okay.
So in other words, you could simulate, you could say, you know what, let's make this even easier. Now, what the hell, I was going to take away the cards and the genders, but you know what, it's good discussion. Leave it up there. Leave it up there. That's what the binomial distribution would look like. If I went and told Max to buy 3 birds, and they were 50-50 likelihood of getting a girl or a boy. So in other words, if we had bought 3 birds from Lava Ridge School that they raised from eggs, unsexed, this was the distribution. There's a 1 in 8 chance they're all going to be girls. There's also a 1 in 8 chance they're all going to be boys. There's a 3 in 8 chance they're going to get 1 boy and 2 girls, and a 3 in 8, 2 girls and 1 boy. You can calculate this using distfill. We actually did calculate, I think, this using distfill last week. If you raise the number of birds bought to 5, it looks like this. We actually skipped over 5. We went from 3 to 4 to 10, I think. But this is what 5 would look like. And you can create all these using distfill. These would all be binomial, 0 through whatever, with a 0.5 probability. That's all. If you bought, there, that's Max and his Crocs from last week. That's Max and his Crocs, assuming he was guessing, right? Assuming he was guessing. Half the time is the most common result. It happens about a quarter of the time. How many times did he get his Crocs on the correct feet? Do you remember?
9. No. 1.
Once. So we decided that that probability is so small that this curve is probably wrong to describe what he's doing. He's probably not guessing. He probably is thinking that those shoes on those feet were correct. Because this is such a small part of the curve, it's unlikely to happen. Good. What if I watched him more? What if I watched him 25 times? It would look like this. Again, all of this can be constructed using your distfill program on your machines. All of these can be constructed very easily. Tell me how these shapes are similar as we go from 3 up to 25. How are they similar, friends?
Bell.
Ah, good. How else are they similar? But go further. There's 50. There's 100. That's a beautiful looking bell curve, isn't it? Yeah. If we proportionally extrapolate Max getting his shoes correct 1 out of 10 times, if he proportionally keeps that pattern up, it will be 10 out of 100, right? If you look at 10 out of 100, it's essentially not on this curve at all, is it? Yeah. So essentially, we don't think he's... I didn't watch him 100 times, I only watched him 10 times, so I can't really do that. It's kind of cheating if I do that. But yeah, it's a bell curve. Meaning we've got some beautiful symmetry, yes? Where's the average? Halfway through, yeah? Where's the median? Where's the mode?
Same.
Hopefully that bores the hell out of you because we talked about it 6 weeks ago. But yeah, when you've got bell-shaped data, you've got the mean, the median, and mode essentially the same. Now these are perfect distributions. Life is full of non-perfect distributions. Let me just show you a couple. Here's 100 randomly selected American women ages 18 to 24. That's their heights graphed in a distribution form. It looks like we broke them down in 1-inch increments. So 60 and a half to 61 and a half, 61 and a half, 62 and a half. Would you call that bell-shaped?
No.
I would. It's not perfect. But do you see how it has the characteristic of a bell? It's not perfect. Okay, so those of you that said no, good, because it's not a bell shape. But statistically it is. It's arguably a bell shape. It's just that we only have 100 of them. So you got to have some noise to kind of play with. Fair? Okay, hold that thought. You've seen these data before, if you remember from back in the day. Menzel, Veronica, Veronica, go!
So you said you would calculate that last graph statistically as a bell shape.
I would call that a bell shape, yes, and then therefore use the properties of such.
Okay.
Just like, remember how, thank you for this question. Remember how last week we talked about the chickens versus independent versus dependent sampling. And we know that when Max picks up the chick, it comes home with us. So it is not sampling with replacement, it's sampling without replacement, right? But we said we're going to treat it as sampling with replacement. Why?
Because there are so many.
Because there were so many and we were drawing so few. And the math is so much freaking easier when you do it with replacement. If you don't do it with replacement, just so you know, if you don't do it with replacement, you have to use that guy. That guy's the without replacement, the pure without replacement. But since you have, I don't know if you can see, if you can see that right there, it says going to infinity.
Yeah.
And beyond.
That's, as n gets larger, that's when you can start using the binomial to stand for it. See, that's what we were getting at that, and that's what Macaulay just said. When you have a large population, you're on a small sample, go ahead and use the binomial. Same thing, Veronica, right here. It's not perfect. It's never gonna be perfect. but it's perfect enough to use the math behind. Is that fair?
Yeah.
This is where I'm pushing you guys out of that math comfort zone once again. You want things to be. I just had a discussion with some OSU students. Hi guys, if you're watching. They're having a discussion with their prof over at OSU, who's using a very specific formula to do a calculation, but there are other ones that are also used statistically. And like, I can't make mine match his. I'm like, well, just use this one over here. Oh my God, how can you do that? I'm like, I don't know, but it's used. Like, I don't have a good answer, but it's used. But it's that math, though. It's that math. I can't make my answer match yours. And we'll fix it by the end of 244, if you're still kind of feeling those twinges right now. You've seen these too! Oh!
So, wait, so they're using this one formula, right? And the guy couldn't get it to go.
So because their calculation was using this other secondary formula.
Right. So
it was close, but not the same.
But you gave him another formula to get the same result?
No, I gave them a formula to explain why theirs was different than his. He was using one version of this. It's called a degrees of freedom calculation for a t-distribution, if you care, which I don't think you do, and that's okay. You have to figure out the degrees of freedom, which we'll talk more about in 244. There's two ways to do it. There's the old school way and the newer school way. He was using the older school way, and the new school way is called Satterthwaite's formula. And I knew as soon as they told me what the problem was, I'm like, I know exactly what's going on. It's Satterthwaite, because Satterthwaite is what technology uses to do it. But the old school way is when you do it by hand. But nobody does it by hand anymore. I shouldn't say that. Obviously, someone does it by hand because it's causing a problem. But hardly anybody uses the manual calculation anymore. They use Satterthwaite's, and that's where
That's what I'm saying. There's two different formulas to get the same result.
No, they get slightly different results. Not kind of like the difference between using the third gender of the chick and not using the third gender of the chick. The chick. But the students were getting so upset because their answer wasn't matching exactly. They wanted to know why. So mathematically, here's why. Then they would calm down a little bit.
Why don't they just ask the professor?
I don't know that answer to that question. Why didn't you? I don't know. Maybe they'll email me later and tell me. LDL readings, you've seen these before. I had you look at these last. I asked you to approximate where you thought the average was here, yes? And you told me the average was roughly, this was 6 weeks ago, but you can figure it out right now, can't you? It's about 5, it's right there. Is it a bell curve?
Yeah.
Who said ish? Thank you. Yes, arguably ish, it's a bell curve. It's got a tail, it's got this hump, and it's got this tail. It's got some holes, of course. You only sampled 100 of them. Is the more you sample, the more it's going to fill in. Thank you. Here's 100 IQs. We're actually going to talk about this starting today. That look like a bell curve?
Yeah.
It does. I'm not exactly sure what IQ measures. Well, actually, I take that back. I know what it measures. What does IQ stand for?
Intelligent quotient.
Intelligence quotient. What is it the quotient of? It's a good damn answer. What does quotient mean mathematically? Kelsey, go. I'll take a drink though. Sorry, I didn't interrupt your coffee. What does quotient mean?
Divide.
You have to divide something by something. Thank you, sister. What are we dividing to make an IQ? You know? Cheese. Cheese. We're dividing cheese by what? Curds? No. It's mental age divided by chronological age. Take your chronological age, whatever that is, put it in the denominator. Then you take some kind of a test and put that score in the numerator. That's your mental age. You do that division and you get a decimal. Change it to a percentage and you get your IQ. That's why the average IQ, look at that curve. What's the average IQ? 100. The average IQ is 100 because that means your mental age is the same as your chronological age. So you are average IQ. It also explains why very young kids can get extraordinarily high IQ readings on their tests. Suppose you give an IQ score, don't you dare do this, to a 4-year-old. Okay? And they test as a precocious 6-year-old. What's that kid's IQ?
150.
150. He's essentially, or she essentially, is off the charts. Off the charts. Now, how many 4-year-olds have you met that act like 6-year-olds? It happens all the time, doesn't it? It happens. Precociousness, it happens. It also shows you why somebody like me is going to have a hard time testing at 150. Because I'm 40 and I have to test like a 60-year-old. What does that even mean? I don't know what that means. I don't know what IQ means, to tell you the truth. I just know how it's calculated. And because I know how it's calculated, that means we can analyze it. And we can talk about how it's then broken down and used. I don't know what it actually implies. I've heard the dolphins are more intelligent than us. I've heard that. I know my son is more intelligent than me. but I don't know how it's actually used. A lot of statistical studies use IQs in their analysis. I'm not sure why though. I think it's because, like the politician thing, it's a measure. It's a number that we can assign a value to, but you have to ask if that number is actually meaningful. And you have to ask your psych prof stat. I don't know the answer to that one. But I do know how it's calculated, and we all do now. And we can analyze it later in class and definitely on Thursday.
Where'd you get your dolphin info?
I just heard that. I didn't get any advice. That's conversationally. Dolphins are more intelligent than us.
I've worked with dolphins and they're evil.
They're evil. Well, evil, intelligent, potato, potato. More like you're ruining my childhood.
Yeah,
Don't tell Max that. He likes feeding me.
I don't know. For every one story you hear about like a dolphin saving,
Gotcha.
There's like 10 where they drug them out.
No. I'm not talking about saving. I'm not talking about goodwill. I'm talking about intelligence. I'm talking about the fact that they can hike together, make bubble nets and things like that, because I guess that's just Darwinism.
They are.
We can chit-chat about this. Though they are evil. Okay.
No, they're intelligent.
Oh, but they're evilly intelligent.
Yes.
Okay. He hasn't blinked in 45 seconds to live that story, FYI. It's terrifying me right now. I want to change the subject. He hasn't blinked? I don't know. It makes me nervous, though. Because I just keep getting bigger, not blinking. Here's some other things that follow bell shapes. Look at some of this stuff, friends.
Wow. Jeopardy, really?
Win streaks, that's just so goofy, I don't even understand, yeah. I don't have graphs for most of these, unfortunately, but I've seen the data sets on quite a few of them. Chips and Chips Ahoy cookies. Egg incubation times for chickens. Huh? Egg incubation times for chickens. Gas mileage for cars. Sizes of wine bottle corks cut by a machine. Somewhere up there, if it's not up there, is amount of fluid in a 12-ounce soda or a 16-ounce soda or an energy drink, or this is a quart, I think. Maybe a little bit less. Maybe it might be 20 ounces. This 20-ounce bottle is not 20 ounces. If you make 1,000 of these, if Hydro Flask made 1,000 of these, and I actually measured precisely their volume would average probably a little bit above 20 ounces. We'll talk more about that in 244 and why they do that. But the actual volumes would be bell-shaped like this. All these things follow bell shapes. One of my favorites, one of the students found it last time, I'd forgotten about this one. The one about times of eye contact with schizophrenic patients. Amazing stuff. Wait lists at COCC. Wait lists used to be. They've changed now. Back when we had wait lists every term for all the classes, I used to graph them just to see if I could predict what they were going to be. Almost perfectly bell-shaped from term to term. The average would change. Sometimes it was 7, sometimes it was 15. Now we don't have that many wait lists anymore, so it's fallen away. But it used to be back in the day when we were at our crazy growth period. Here's another one for you. I just fixed this. Hopefully it works. It's a YouTube video. I may have to go out and search for it. Oh, it didn't work. Hang on. I have to go out and search for it. I thought I fixed it. Embedding YouTube videos in PowerPoints is proving to be my nemesis. So I will find it for you the same way I found it an hour ago. Maximus Omzi YouTube. There he is. Check this out. Yeah. Come on, IT.
It's pretty cool, like, what do you...
Oh, volume. You have to hear him talking. He's explaining it to you. Oh, I can't hear. He's explaining the whole thing to you. Oh, well.
It's the bottom right. Yeah.
Oh, my God. Now, why can't I just change that? Whoa! So now we have 3 volumes. This is wonderful. This is technology at its best. 3 different volume levers. So have you ever seen this at OMSI? How many of you guys have been OMSI to see this? A couple of you. He's about 3 when this happened.
Oh yeah?
So what's happened, they're taking these little tiny white pebbles, little tiny white pebbles, up to the top. I'll have a shot up in a second, you'll see it. Dropping them from the top in the middle, they're bouncing off little pegs. There are pegs up here, set at a grid, a square grid, and the balls are hitting them and bouncing off pseudo-randomly. I mean, definitely randomly to some degree. And they're placing themselves in that bottom grid. Now check it out. I'm going to jump here in a second. I cut the video and then re-upload it later on. Max, checking it out. There, that's later on, in the same exact trial. So you see what's going on. They're getting dropped up there, they hit here, and then kind of randomly fall down. There's my wife explaining it to Max. So sometimes they land over here. Sometimes they land over here. They always make that noise. Thank you, Jen. But on average, where do they land? On the middle. Why? Why on average do they land in the middle? Say that again? But yeah, but it's bouncing off pegs. No, Di, hear what Di said? Well, yeah, I asked, why on average do they land in the middle? And she said, because you're starting in the middle. And I said, yeah, but why? And she said, oh, I know. I'm like, no, you got it. But why, if they start in the middle, on average, are they ending up in the middle? I mean, they're bouncing off those little pegs, yeah? They're bouncing left, they're bouncing right.
But there's only so many little pegs they're going to bounce off because they're going
It's
down.
all about the likelihood of where it goes once it hits a peg. On average, think of it this way. Every peg that thing hits as it goes down is like a variable in the construction of a chicken and its egg. Is like the variable in the construction of that little bottle right there, or a gas tank in a car. Whenever you make something in a system, whether it's a ball falling through or whether it's a bottle being formed, there's little tiny micro adjustments that happen. And generally, they even out. For example, if a hammer hits one too many times, automated hammer hits one too many times here, chances are it's not going to hit one too many times every single time on the same product. Sometimes it does, and that's why the ball ends up way the hell over here or way the hell over there. But generally, for every left turn the ball makes, it's canceled down the way by a right turn. That's why, this is my explanation. Now, there's a mathematical explanation if you want it, it's on the enrichment page. But the non-mathematical explanation is, generally, on average, every left turn is canceled by a right turn. Which goes back to, if you think about it, it goes back to, shut you down, it goes back to this idea of the binomial. It goes back to this. With a probability of 1/2, generally you land in the middle, on average. You can land slightly left or slightly right. But the further you get from middle, the less likely it is that you land there. Because if you get too far left, that means you made more left turns than rights. While possible, that's not probable. Exactly, and it's symmetrically opposed on the other side. You'd have to make more right turns than lefts to end up over here. While possible, it's not probable. So Max in his shoes guessing. This is why I don't think he's guessing when he puts his shoes on. If he was to guess 100 times and only get them right 10 times out of 100, sure, it's possible. It's possible. But that would mean for every right turn he made 9 left turns to get over to this side. If you think of it from a slope point of view, 1 right, 9 lefts. 1 right, 9 lefts. Eventually he gets over there to 10. Well, that doesn't sound like guessing, does it? That sounds like he's weighting the left side of the curve. Now, sure, it can be over here. It's just not very likely over here. And that's the idea. Does that kind of make sense? Ish? So all of these things that you see right here, if you think about how they're constructed, a ball bearing, think of the process where a ball bearing is made. Within the past year, I realized that a BB, like a BB gun, BB stands for ball bearing. How the hell I went through 40 years of life without knowing that? I mean, I've been using ball bearings. I've been biking for more than half of my life, so I've rebuilt hubs a number of times. I'm always putting ball bearings in the hubs. And somebody goes, hand me those BBs. I'm like, BBs? They're ball bearings. I'm like, yeah. And then it was like driving across Oregon on 20 and seeing the Ore-Ida factory and going like, oh my God, that's why it's called that. Because it's on the border of Oregon and Idaho. Again, it's like, oh, the skies open up, and it's like, oh, here's some information that you now have earned. It's one of the things. You don't remember anything else today except that. So, but if you think about all these chips and chips away cookies, body temperature, hip breadth, lifespans of computer components, if you think about all those things are created through a process. All those processes have little tiny fluctuations. What the bell curves kind of imply is the fluctuations that fluctuate too far to one side are balanced by fluctuations to the other side. Does that kind of make sense? All these things are constructed like that. Whether it's a person, a ball bearing, a gas tank, a bottle, a schizophrenic patient, whatever. All those people, things, objects are created through a process, and the process has variation. The bell curves kind of guarantee us that the variation balances. And what I find the most amazing about all of this is the Germans, before the Germans had the euro, they used what was called the mark system, M-A-R-K, the mark system of currency. We put things like presidents on our money. You know, George Washington, Abe Lincoln. What do they put? They put mathematicians on their money. Why? Because they're geniuses. And not only that, they put bell curves on their friggin' money. Look at that. There's a bell curve and its equations on the $10 bill. Who's on our $10 bill? Actually, who is on our $10 bill? Is that Hamilton? Is that Hamilton? Okay, I'm gonna call it Hamilton. Who cares? What did he do? He didn't prove the central limit theorem. Actually, Gauss didn't either. This guy did. This was De Moivre. He got his picture on a little penny. And that's okay. Abraham De Moivre got a penny. I don't even know what country it's from, but that's okay. Probably France, because he's De Moivre. So, cool. Let's take 5. We'll come back and show you how to actually use this. Because Monica brought up a good question. Like, what's the point? Let's find out. Let's find out why we like to make things bell curve.
I want to know if, did Max know that there was a right and left shoe when he was putting him on?
Oh, I have no idea. I never asked him.
So if he did, then he was guessing. Otherwise, he just put shoes on.